G'day. So thanks to everyone for coming and joining us today. I'm going to give you a brief rundown on the indicators work that Kayla mentioned before we get into the details for Indonesia, just so people have the concepts in mind. Next slide, please. And next one. So this is a body of work that's grown out, has grown out of about 8 years of work across a large number of people around the world. It's definitely a joint effort, and it's good to see it come this far, but just acknowledging it's just not me. There's a lot of other people involved. Next slide, please. Primarily, the works happened in the Eastern Bering Sea, North Central Chile, Indonesia, and Australia initially, and now has grown into the Gulf of Thailand and Sala Bay. And it's great to see some of the results of that starting to flow through. But those locations were initially, sorry, my dog is now barking in the background. Initially, it was chosen because they are very different kinds of ecosystems and very different cultures and expectations from their ecosystems. So we're trying to find a way of looking at ecosystem structure and reporting that into fisheries and conservation management that would work regardless of the kind of ecosystem you're dealing with. Next slide, please. This has been really important because a lot of historical fisheries management focuses on assumptions around if the fishery was just the fish and the fishermen. In reality, most fisheries in the world are actually at least mixed with different species being caught by different fleets, or in actuality, the animals eat each other. So it's a really complicated set of connections. And that historical kind of fisheries practice isn't going to work. So we have to find a new way of doing things. So we worked with managers and research scientists and policymakers to find something that would work. Next slide, please. One of the assumptions that people often see is that they've learnt about maximum sustainable yield from a textbook or a course, and they assume that if they go and do that for each individual species in these really species systems, that that's going to work, and somehow that you can take all of those individual maximum sustainable yields at the same time. And the reality is just very different. Indeed, if you fished at max at the by taking the maximum sustainable yield of each species at the same time, you would massively overfish a system, which you can sort of see here. That dotted black line on the left-hand side is the maximum multi-species yield, so the real maximum that you can get out of an ecosystem. And you can see its peak is much lower than if you add the individual dots together on those big linear lines. So we're really trying to find a way to help people stay within the bounds of an ecosystem level of exploitation. Next slide, please. Now, we want to myth bust right from the start. It is possible to do EBFM regardless of what ecosystem that you're in. You don't need to have heaps and heaps of data. You can tailor the indicators that you use to the data available. And I'll touch on a few of the sort of data light ones at the very start. But the bulk of what I'll talk about is it assumes that you'll have catch composition and some food web information. Now, you can use these indicators with data if you've got it, but you will need data from an unfished reference location or from history. So it's more likely that you're going to rely on ecosystem models for at least part of it. But in theory, you can do all of this just with data. It doesn't have to have a model. And it also links from that strategic guidance of management right through to tactical decision making. Okay, next slide, please. So the first concept to get your head around is called hub species. So the reason they're called hubs is because the idea came from the same methods that people use to look at weaknesses in transport networks or distribution networks or the internet. So the idea of a hub being somewhere where a lot of flow goes through, and if you lose that critical bridge or you lose that critical internet server, then the whole thing goes down. So using those exact same methods, running it over a food web where the individual nodes are the species and the edges or the links between them are their feeding or habitat interactions. Next slide, please. So if you do that, you can find that there are some key species that if you take them out of the system, the functioning of the system degrades really quickly. And that's because ecosystems evolved to transmit energy up through them as rapidly as possible and to be robust to a random loss of species through time. But they have these key links that if you lose them, the energy flow just isn't going to work as well, and you get very large scale change in the ecosystem. Some of these species will also be recognised as keystone species, but it is a different concept. It's not a one-to-one mapping. What you often find is that they're forage species or prey species at the bottom that support a lot of the web, or connecting species at the top, really high top level predators that connect across the system. And they're identified based on their feeding connections. There's some mathematics behind that I'll save you, but that's the basic idea, what's holding those systems together. And once you've identified them, you can put additional management precaution around trying to make sure that they're maintained. Next slide, please. Using that exact same information and some advances that people have done around networks, you can also see how resilient that network structure is. And that comes down to the amount of flow that's going through the network, and how diverse that is across different pathways in that food web, and the number of connections in the food web. The more diverse the food web is in terms of the number of connections, the more connections and the more pathways that the energy is flowing through, the more resilient the system is. If you lose connections or you lose that diversity of flow, you become partially resilient. And if it continues to decline in either of those dimensions, you will eventually pass a collapse frontier. And that means that the structure of the system simplifies dramatically. You may well still have an ecosystem there. It may still have some species around, but it won't be as diverse and it won't have as much energy flowing through it. It won't be as productive. Next slide, please. The last idea to get your head around as a component is around distortive pressure. How are you putting pressure on the system? Does it match the kind of pattern of pressure that you would see in an unfished system? So the idea is that without fishing or other human disturbance, there's a pattern of the ecosystem has been ticking along under a pattern of predation indefinitely, or at least for long periods of time, and that pattern of pressure is sustainable. So if you take that pattern, you take the slope, you plot it up as biomass versus production. The slope of that line and the spread around it tells you the pattern of fishing catch that'll be sustainable in a fished system. So if we have the next slide, please. So that profile there. So the green band is the safe spot. That means that pattern of catch, fishing pressure, looking at catch versus production, would match the predation pressure. So you're not putting too much pressure on any one part of the system so that it's in a different pattern to that predation that it was effectively evolved to withstand. Next slide, please. So the slope of that regression in the biomass one comes over to be the slope of that green band, and the width of variation around that predation, the blue dots, relates to the width that your green band ends up. Next slide, please. So once you've got that green band, then you put on how much you actually fish, and you look to see where the individual species fall. Are they sitting inside the green band, in which case you're not putting distortive pressure on them? Are they sitting under the green band, which means that you've got a little bit of scope to increase your fishing pressure on those groups? Or are they sitting above the green band? And that's the orange dots. And that's when you're overfishing a system in the sense of putting too much pressure on one part of the system. You're causing a structural distortion. Now, you'll notice that there's a single black line there, and that's actually the level of fishing pressure that single species fishery science would suggest is a sustainable level. So you can see the lower productivity species will actually still have distortive pressure on them, even if you were complying with single species management. And this is where that disconnect between a multi-species and an ecosystem approach and the well-intentioned single species approach. So this does help you bring the two worlds together. And so you could do single species management and just check it in this way and say, am I complying with that green band or not, even if I didn't do anything else? That would get you closer to EBFM. Next slide, please. And you can track that through time. This is an example from Southeast Australia where some of the species were moving up into that green band and then going beyond it, and then the management measures had to try and bring it back within that green band. Next slide, please. You can think about each of those components separately, or you can actually combine them together. So just as in Australia, we have a warning index around bushfires or floods that bring together all of the exposures and pressures to say, this is a good day, there's not going to be any bushfires, or no, this is a day where bushfires might be at risk. It would be really handy to have that kind of warning system for ecosystems. So that's why we combine these different indicators together to give you that one measure. So it brings together the idea of the hub species and the topology of the system, how resilient that structure is, and whether you're putting distortive pressure on it. Next slide, please. So it has a 10-point rating, which sounds a lot, but in reality, you can just think about the four colours. If you're in the greens, you're fairly lightly fish system. You can just keep monitoring. You don't really need to change what you're doing. In fact, you could increase fishing. If you're in the light yellow, then you're in a pretty good fishery state. You would want to keep monitoring, but you don't require any change. Once you start to get into the orange, you don't have to respond immediately, but you're going to have to start reporting in some stronger management and pay attention to what you're doing in the ecosystem. But the ecosystem should rapidly respond, and you should be in a good state again pretty quickly. Whereas if you get into the red, you really need urgent intervention. If you're going to maintain your ecosystem structure and function, it would need to be really large scale change. Next slide, please. And you can either plot that as a once-off, as we've done for different systems around the world, or you can try and look at it through time. And this is an example actually from Thailand, tracking how it's changed since 1950, both in terms of fish down effects, but also recovery once management has started to be put in place. Next slide, please. So that's pretty much it for me. It's about changing your point of view so that you can deal with the fact that you don't need to be focusing on one species at a time. It's not about trying to replicate historical management for fisheries for thousands of species all at once. It's about leveraging that systematic nature of the way ecosystems work and using that to tell you whether you're really aiming for EBFM or not. Next slide, please. And I think that should be me. So I'll hand over to probably Irfan and the rest of the team. Thanks.